There are three theorems that you have to know, which come up as so-called mandatory theorems. This one is Theorem 11, and it forms actually the backbone of Theorems 12 and 13. So it states that prove that if three parallel lines cut off equal segments on some transversal, then they will also cut off equal segments on any other transversal. So how they work this is that you have to have a diagram. So what we're going to do is we're going to have three parallel lines. Uh, I guess we'll just call them L, M, and N. So instead of L for line. What we're also going to have is we're going to have two transversals, sort of like this. Uh, Normally these transversals are called S and T, and the points where they intersect are A, B, C, and then D, E, F as well. Now, the next thing you're given is given. So we're given that L is parallel to M, which is parallel to N, and we also have transversals S and T intersecting A, B, C, D, E, and F. Now, to prove, oh, actually, I forgot one thing in the given. Oops, is actually that we're told that or we can assume that AB equals BC. Okay, now we get to the proof. So what we want to show is that DE equals EF. So I'm actually going to put these little lines in here. So what we want to prove is that DE is equal to EF. Now the trick with this is that you draw another transversal, and this in red. I'll call this transversal U. U intersects two places. So we're going to call the points X and Y where it intersects. It goes through E. So what we're going to construct, therefore, is transversal U parallel to T to S. Oops. Parallel to S uh, through E, and then it cuts L and N at X and Y, respectively. So that's what we have here. So we can indicate with arrows, I guess, that the S and U are actually parallel to one another. So now we get onto the bit of the nitty-gritty. So what we can say is that BCEX is a parallelogram. So this is the proof. Is that BCEX and ABEY are parallelograms because you have sets of parallel sides, because we intentionally made S and U parallel to each other, and LM and N are also parallel. So if hold AB equals BC, that's what we're given. So now what do we do? Well, we can say that because they form parallelograms, AB is the same as EY. For a start. Likewise, BC equals EX. Just a start. So because AB equals BC, both of these statements imply that EX is the same as EY. Now with EX equaling to EY, we can actually now compare triangle FEX and DEY. So now we're going to compare FEX and DEY. So this we can label as a congruent of sides. Now, because these are vertically opposite angles, FEX equals DEY. So magnitude angle FEX equals magnitude angle DEY, and that we can label as our angle. So that's these angles in here, they're the same. We can also spot that we have some Z angles here and here. So this is going to be FXE and EYD. So FXE and EYD, which is another angle. So therefore, triangles FEX and DEY are ASA congruent. Therefore, the lengths DE and EF must be the same. And that's Theorem 11 done.